Okay, let's begin with the first problem on this worksheet that I asked you to print out and read through it. It says the size P of a certain insect population at time t in days obeys the function P of t equals 100 e to the 0.01 t power. Now this is very similar to the formula that I talked about in the last video. And instead of A's, we're using the letter P. So what are we given as we talk about this problem? We know that we are starting with 100, and this is insects. So our amount of insects that we are starting with is 100. So that is the answer to part A. The number of insects at t equals 0 days is 100 insects. And that is always the initial amount when time equals 0. If you would like to take this formula and put it in your calculator, putting a 0 in for t, we would have 100 second e to the power of 0.01 times 0, and you get a 100. So if you want to just substitute in t equals 0, you'll get the same thing. But this is our initial amount of insects, 100. We want to know the growth rate of the insect population. And the growth rate is our K. In this case, our growth rate is that 0.01 that occurs before the T. So our growth rate is 0.01, which means 0.01, if you change that to a percentage, is you would move the decimal over 2 places to the right or multiply 0.01 times 100, and that would give us 1%. K is positive, so 1% growth per day because T is in days. So our growth rate is 1% growth per day. Now let's see what the population is after 10 days. Well, after 10 days, our T equals 10. So just take your formula and plug a 10 in for T in the calculator. And you'll get a solution. And I got 110.5. Well, you can't have a fractional amount of insects, so we will round that to the nearest whole number. 111 insects. So with this growth rate, we started with 100 insects, and after 10 days, we now have 111 insects. Part D. When will the insect population reach 140? Well, that's the amount at time t, and this says when, so we don't know our t. We're going to take our formula, and for population, we're going to put in 140. And solve that equation. Now this is an exponential equation, and we've talked about exponential equations. When you solve them, you need to isolate the term with the exponential portion. So I need to divide both sides by 100, and I have 1.4 equals e to the 0.01 t. And now that I have that exponential term isolated, I'm going to rewrite this in logarithmic form. and that would equal log base E of 1.4 equals 0.01 t. And then to solve for t, I will divide both sides by 0.01. T equals, log base E is the same thing as natural log, so that's ln of 1.4 divided by 0.01. So now it's just calculator work, and I will do natural log of 1.4 divided by 0.01, and I get, if I round to the nearest tenth, I get 33.6 days. So in 33.6 days, we will have gone from 100 insects to 140 insects. Now part E says, when will the insect population double? So for part E, we are just going to put what the population would be if it doubled, and if it starts out with 100, if it doubles, it's at 200. So 101 t. 200 equals 100 times e to the 0.01 t. And I'm going to solve it just like I did part D. I'll divide both sides by 100, and when I get that, I get 2 equals e to the 0.01 t. Now I will write that in logarithmic form. So that would be the log base e, which is natural log, of 2 equals 0.01 t, and then divide by 0.01. And t equals natural log of 2 divided by 0.01, which is about 69.3 days. So it takes 69.3 days for the population to double, and that will happen every 69.3 days.